Hi guys, just give me a minute. I'm just joining in. Hey guys, hi, hello. How you all doing? Sorry for the delay. I'm here, I'm here, I'm here, I'm here. Mm-hmm.
It's not about
Yeah, guys. Okay, A levels. Okay, hi guys. Let's start. Thank you for joining in. We got a fewer people in today. Hi Ramesh, Mesam, Haya, Hassan, Hanan. Okay. Anyway, so where are we at? Where are we at? Where are we at? Okay, so I got to share my screen also. We're doing finishing up what we did last time. Energy changes. That's what we're finishing on today. I got to share my screen also with you guys, and okay, Walaikum Islam. Zoom is coming. Yeah, I'm on Zoom right now. Arisha, we are on Zoom right now. Isn't that the? It's the same link from last time. Yeah, the Zoom link is the same one from last time. If you have that, all right. And all right, I use a Rode mic, pod mic, and a Blue Yeti simultaneously, two mics. That's what somebody was asking me. For those of you who can see this on Zoom, this is on Zoom. We are on Zoom now. Yes, Walaikum Salam. Haya, I'm great. How are you doing? Absolutely great. I am too. Yes, Arisha, it's the same link from last time. So we left off at energy changes. We're going to finish it today. That is, I don't have any affiliate links. Agastya. Yeah, I just don't. I don't have them right now. I have no affiliation or anything yet, but I like Rode mics. I really like Rode mics. So, yeah, I use those. All right. Yes, Moise, this is an O-level class. By shouting electrochemistry A2, I'm now going to be starting electrochemistry A2 right now. You do realize that, right? Thank you for shouting. I couldn't hear it before. Yeah. All right. So, yeah. So if you remember, we had two kinds of graphs, and I want to mention this to you guys. That's what we're starting off with, right? All right. Okay, so you see my screen? Yeah. Let's start this recording also on Zoom. And I'm going to begin now. Yeah? Arisha, welcome back here. So, in the last class, we saw what? So in the last lesson, we left off at seeing the two kinds of reactions. One was called exothermic reactions and one were called endothermic reactions. Now, exothermic and endothermic. The first thing is that you need to know for the exam is, are you able to identify the reactions which are endo and exothermic from their energy profile diagrams? The most simplest version is using reactants and products and seeing how they interact. I mean, how they are on the energy scale. For example, here would be a graph of an exothermic reaction. You've got energy on the y-axis, and now this energy represents the internal energy, also what we had called chemical potential energy. And then the other was endothermic, and endothermic reactions had so the difference first is that in exothermic reactions, reactants have greater chemical potential energy and products have lower chemical potential energy. And this idea that energy is given out is really the internal energy being converted to heat energy. Most cases mein it's chemical potential energy converted to heat energy. Now, in sometimes you can even release energy of a reaction in terms of electricity. You can release it in terms of sound, light. So all forms of energy, it's a conversion from the internal energies of the chemicals to externally measurable energies out there. All right. And we saw endothermic also. I'm going to bring that up also for you guys. Right. So, for example, I'm just pasting it here and then bringing it up for you guys to see visually. So now this is the endothermic part of the reaction, endothermic reaction. The difference here is that reactants have less energy than products. In exothermic, reactants have more energy, products have less energy. In endothermic, reactants have less energy, products have more energy. And to go from reactants to products, energy is taken in from the surroundings. Generally speaking, what this means is that the heat of the surroundings is converted to the internal chemical potential energy of the chemicals. Reminder, the y-axis energy is not heat energy. It is a measure of the internal potential energy of the chemicals. That's what it is. Yeah? So far following? Any questions on this? Yeah? Yeah, you don't get the video today. You get it tomorrow, Arisha. Yeah, I'm sorry. Everybody all good? Everybody all good? Mm-hmm. Uh-huh. Mm-hmm. 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 Yes, yes, and yes. So, all right. Is that okay? So far, so good? Anyways, so moving along, where were we? So the first thing is that you have to know that. All right. Now this is the most simplified version of seeing an exothermic reaction and an endothermic reaction. In most cases, it doesn't just go from here to here. It's a little more detailed, okay? And it involves something known as activation energy. One second. Any questions so far before I move on to activation energy? No, nobody. You have to not, but that question. Okay, first of all, please put the question to either panelists and attendees so everybody can see the question, or to just the Q&A section. If you just write panelists only, I'm not gonna be क्या कहते हैं wanting to answer that, because nobody else will have to repeat the question. It's a painful process, Ramesh. You don't have to memorize the question. Graph, yes, you do have to know that the products are lower than reactants in exothermic, and the products are higher than reactants in endothermic. If that's what you mean, then yes. If that's what you need to remember, yes, you do need to remember that. You need to learn that. Yes, sorry, Bob. Absolutely. Absolutely. All right. Thank you, Harun. You're very welcome. That do it for everybody. All right. Yeah. Okay, so we move on. Hi Dilavar, how are you? I'm great. Yes, I'm great, love. I am great. So let me say this explicitly. So for you guys, you have to know this for exothermic reactions. Exothermic reactions are those where the internal energy of chemicals is converted to heat energy and released. Now in this case, the temperature, one feature of the exothermic is the temperature increases and it gets hotter. On the other case, endothermic is what? Is the opposite. You have what was I saying? The thermal, basically the heat energy. So the heat energy or thermal energy of the surrounding is converted to internal energy of the chemicals. Now, internal energy of the chemicals doesn't make the chemicals hot. In fact, everything becomes cold. The temperature of everything drops. It gets colder than what it was before. Let me write the word colder again. Colder. All right. So far clear? Yeah? Then I gave you a couple of exothermic reactions. Remember, was natural gas burning to form carbon dioxide and 2 moles of water, acid and alkali reacting to make water. Those are exothermic reactions. And endothermic reactions ka very good example is decomposition. When you heat something and it decomposes to become something else like calcium oxide and carbon dioxide. This is calcium carbonate, also known as limestone. It's a very popular reaction for decomposition. Okay, it's endothermic. You might, because you have to heat it, you might say, well, how does it become cold? But we get into the heat part right now. But we'll get to that part. Okay, why does you have to heat this reaction? Sometimes you have to heat reactions, but because that's what I'm getting towards now. Why do we have to heat certain reactions? We have to heat certain reactions because they require a certain minimum energy to take place. Okay, yeah, and that minimum energy is called activation energy. So now the next thing we're looking at that is started off with is that we're going to look at something called reaction profiles, meaning exothermic and endothermic reaction profiles. To talk about reaction profiles, first I've got to introduce the idea of activation energy. So activation energy. Now you notice something that I talked about. Okay, there's an endothermic reaction that we saw was called calcium carbonate is endothermic, but to perform this reaction you have to provide heat even though the reaction is endothermic. Why do you have to provide heat? Because this heat is provided to overcome activation energy. And it's not only an endothermic, it's also an exothermic. Many reactions have what we call activation energy. Now what is activation energy? So this is the minimum energy required for a energy required of the particles. So the particles have to have that energy for a reaction to take place. It's the minimum energy the particles must have if they want to react. It's called activation energy. It's the minimum energy the particles must have for them to react. Sometimes some reactions need energy to kick off, and we'll get to that also in a bit today. But some reactions need a minimum energy, and that energy is called activation energy. So for that means that when we talked about this graph, guys, right here, reactants don't just only release energy to become products. Sometimes they first absorb energy called the activation energy and then they release it. The calcium carbonate one had to become a product, but it had to absorb a lot more energy and then become a product. And so I'm going to show you those graphs now. The energy profile graphs of endothermic and exothermic graphs that outline what's happening to their internal energy, but also in terms of activation energy, because we need activation energy for a reaction to take place. Yeah, let me show that to you. Just 1 second. Any questions till I bring that up? None? Anybody? Nobody? All right, moving along then. There's no questions asking. There is. Okay, so there is no way to figure it out. They'll tell you or they'll be shown to you. Dilawar, we didn't study anything to do with energy in reactions. Now everything to do with energy we're studying in this chapter together, which is the overall energy change and activation energy. Before this, we didn't introduce the idea of energy, so that's why we didn't study it in reactions. But you never will be quoting the activation energy वैसे ही. You won't be. So here is a sample energy profile diagram. Now, it looks pretty big. This is of an exothermic reaction. Now, I can show you endothermic also. This is an exothermic reaction. This is the more common one. Why is it exothermic? Because how can I identify it's exothermic? Because the reactants are higher on the energy axis than products are. And when reactants are higher, products are lower. Which tends to tell me that this is an exothermic reaction. Yeah? That's what you should know. Now, there is something marked here. Now look at the graph. In a normal graph that I showed you earlier, and I want to bring it to your attention also. So let's go back here for a second. Let me bring the normal exothermic graph that we had seen earlier. I want to bring it down for you so that you guys can see for yourself the change, the difference. So earlier I had shown you this graph, and I've dragged it from a top, where there were reactants and they made products. But this is a simplified version. This is the more detailed version. What is happening is, yes, and I might make it even smaller, so maybe it might meet the values, but it doesn't matter. It's the type that matters. So reactants become products. This is the overall change. Energy is given out. But what's really happening is reactants first need some energy to go even higher. They absorb some energy. Because you can think of it like they need to absorb this energy to be ready to react. Because by definition, activation energy is the energy needed for a reaction to take place. Without it, a reaction won't take place. All right? So what's happening here on the graph on the right is the representation of what's happening to the energy, internal energy. So the reactants first absorb heat energy from the surrounding, convert it to some form of internal potential energy, chemical potential energy, and then they react. And then when they start reacting, they start releasing all the energy out. So in a graph like this, there are actually two parts to the graph. There is an energy absorbance part, and then there is an energy release part. So it doesn't straight go down. It's not directly exothermic. It actually is a bit of endothermicness to it, and then it becomes exothermic. The overall reaction is exothermic. Why? Because the overall change is from there to there. It's going from this higher value to this lower value. That's the overall change. But a change in energy from reactants to the highest value is called activation energy. And this overall difference. Now, let me give you this. Let me give fake values. Let's say, and if we knew the axis, let's call this value as 30 for the sake of argument. And let's say this is 10. And this is 45. So if this was the x-axis, y-axis, what do you have? The reactants have energy 30. They absorb a certain amount more. Can you tell me, can you figure out how much are they absorbing more? Ramesh, Dilawar, anybody? Haya, Arisha? How much are they absorbing more? How much they have to absorb the energy to go from 30 to 45? So there, and this is, by the way, let's call it kilojoules, the unit for energy. So they're absorbing 15 kilojoules more to reach this highest point. And now they're at 45 and they have to come all the way down to 10. Yeah? So they come all the way down to 10. What's the energy change? When you go from 45 to 10, how much are you losing? 35. So you give 35. You take in 15 and you give out 35. That's literally what's happening. So you can even say it like math. Like if I'm to measure the internal energy of the particles, they absorbed 15 to go from 30, they plus 15 to go to 45, and then they minus 35 from 45 to get to 10. So here, technically speaking, plus 15 is the activation energy. Do you follow that? That plus 15 would have to be the activation energy. Yeah? Can you hear me? All right. Now, that's that part. Exactly. So this reaction, for it to take place, it would have to absorb 15 joules for it to even start. Like, none of this matters unless it takes out 15 joules. It's sitting at 30. It can't go to 10 directly. It has to first absorb 15 for it to lose 35. Yeah? And what's the overall change? From reactants to products, what is the overall change? It started from 30. Now, after taking in 15 and giving out 35, it's at 10. So from 30, it has to lose what to become 10? Can you guys tell me that? I'm sure you guys can. Yeah? So it loses 20. So it had 30 and 20 is lost overall, meaning the net change is 20 joules of kilojoules of energy. It absorbed 15 kilojoules. That means it took away 15 kilojoules of heat from the surroundings and converted it to internal potential energy and made it 45. Then it took 35 out of the 45 kilojoules and released it as heat energy to everything else around it. So it lost 35 joules. It took 15 in, but it lost 35. The net change is minus 20. So this yellow line is called activation energy, and it's written as EA. EA, activation energy. Activation energy is for this part. And this part right here is the overall change. Now obviously the overall change, if it goes down, it's negative. If it goes up, it's positive. Here it's negative. So you could say the overall change of this reaction is minus 20 kilojoules. Or we say the overall enthalpy change is minus 20 kilojoules here. You're very welcome, Marisha. I'm so glad you've understood it. I used actual numbers to hopefully make you realize. Let's look at a couple of more examples, eh? Now, let me show you basically the overall energy profile diagrams of endothermic and exothermic with this energy going up. All right, let me scroll down. Okay, yeah. Well, Dilawar, as long as you're understanding this, I am so glad. So Mesam, the overall change here is negative, boss. The overall change here is, oh, can it be minus more than, no. See, that's the thing. The energy can never be zero. You understand? Okay. So I know some of you asked this earlier. Let me go back for a second now. So guys, listen. When I use these values, remember that this energy is a scalar quantity. Energy itself can never be less than 0. So this point is 0 and everything else is above that. Only the energy change, overall change can be negative. Individual energies have to be positive. But these values are my fake values given to you to explain. We human beings do not know these actual values. We only know the change. Our labs can only measure the change. We do not know the actual values of things because there is no way to measure the internal potential energy of chemicals. What we only know is to be able to measure the change. So in the lab, only this is measurable, this blue part. All of the things are not. Let me show you the graph again. So basically, let me show you this. Let's go back here for a second. This was me trying to show you the energy profile diagram of an exothermic and an endothermic. First of all, just let's even mark the enthalpy changes. I will use a white line to show you that. So this line from all the way here to here, from the reactants to the highest points in terms of energy is activation energy. Then again, I can use actual values here for why not, right? So let's call this 15. Let's call this 23 and let's call this 51 for the sake of argument, right? So 15, 23, 51, whatever. I just took random values. And let's say this is 16 and this is 47 and this is 25. Because I just couldn't come up with some random number. So this value is 25. So let's use this. So because I think numbers are making it easy for people to see, right? So first of all, activation energy for an exothermic reaction. First of all, how do you know this is exothermic? Because whatever energy reactants have, the products have lower energy, internal energy. So when they go from reactants to products, they are releasing energy in terms of heat to the surroundings. The energy of reactants goes from 23 all the way up to 51. That is the highest point. From the starting point to the highest point, that arrow that I've labeled white is your what? EA, activation energy. Starting point to the highest point is activation energy. And we call it EA. So let me say this here. EA is activation energy. And what is activation energy? It is the minimum energy the particles must have. So the minimum energy particles must have to react. Okay, so if I were to ask you to quantify the EA for this, can you give me a value for the EA for the left hand side? Let's call this EA1 because that's the first reaction I'm looking at. So can you give me a value for this? It goes from 23 all the way to 51. Could you give me that? Thank you. That is absolutely correct. This is 28. Obviously, let's assume my units are kilojoules. So let's write them as kilojoules. 1000 joules. Kilojoules is the unit for energy. Yeah. Then on the right hand side, so this is that fellow, right? This is this reaction's EA. Now let's go here for a second. Let's focus on its EA. Its EA starts off from 16 and goes all the way up to what? $47. So how much does that come out to be? Let's call it EA2. How much is this EA2? Yeah, I know somebody told. It's 31. Awesome. Yes, it's 31 because it's 47 minus 16 is 31. So its E is 28. Its is 31. Obviously, I just made up these numbers, so that's how we got them, right? But it's from here all the way up here. Obviously, right? Okay. Yeah. All right. Then that's the now energy released. Now energy, the unit for energy release, I'm going to do that in let's say yellow. So here the symbol or the symbol for energy release is delta H. And if it decreases, you give it a minus sign. So it's going from 23 to 15. It's decreasing by how much? Can you guys tell me that? I'm sure you guys can. You guys are awesome. You guys are getting this. It's decreasing by 8. So Farwa, it's absolutely right. So delta H for this reaction is minus 8 kilojoules. It's decreasing by 8. So therefore, if it's decreasing, it's minus. And because it's minus, therefore it is exothermic. Because it is minus. And why is it minus? Because the internal energy is decreasing when it goes to the products. Here, the internal energy is increasing by becoming a product. It goes from 16 to 25. So here, how much is this delta H? Let's call this delta H2. This one is increasing by 9. So it is plus 9. We should write it plus 9. The reason why we write plus 9 is to ensure that it is not negative. We knew it's positive. That means it's increasing. And this is decreasing. Obviously, energy cannot be negative, but change of energy, delta H, can be positive or negative. Alright? So, and these are called energy profile diagrams. Yeah? Any questions about this, fellows? No, it's perfect? Awesome. So I know I've given you a lot of diagrams, but I'm overloading the last diagram. This is what we've done so far. There are only two types of energy changes: exothermic, endothermic. You go from reactants to products. You always have to go up first. Regardless of large or small, you're going to have activation energies. If the products are lower than reactants, the reaction is exothermic. The overall change you can say delta H is negative. If somebody asks, how do you know it's exothermic? Because the delta H is negative. This is the activation energy. Here, the reactants are lower and the products are higher. So the delta H here will be positive. And therefore, that's an endothermic reaction. Alright? Yeah? Crystal clear? Crystal clear! Hallelujah! Hallelujah! Sorry. I'm a little crazy man. Okay, we're starting the next thing about this chapter. Well, I'm gonna drink some water. Can I get some water, please? I'll take a 1 minute break to drink some water because I'm constantly talking. Aight. Yeah, I'm back. Yeah, Orisha, welcome, join the club. My accent is off the charts. It is really cool. It is amigo. Amigo. Hey, will you go over A2 electrochemistry? Somebody's asking me from A2's on YouTube. Hey, honey, whatever this is, person. Yes, dude, I've already shared some 6 videos on electrochemistry. I'll find from my archive some more. I forgot to upload them. That was 6 months ago. I don't know where they are. I'll look for them. And maybe I'll find them. Maybe I don't. But you give me this weekend, please. All right. I don't know South American. Yes, Ramesh, see my face. Ramesh wants to see my face. Yes, so, see the problem, Ramesh, is if I have to stream to YouTube, you really can't. If I do this, maybe. That's the problem. Yeah. For now, you could do this, huh? But then people at YouTube only get to see my face and not the screen, so that's another problem. I do Arabic. I do want. I've got to think about it. Yes, I can do a bit of Arabic. Yes, a bit of Arabic. Yes, not too much, eh? A bit of it. Yes, the T's have to be soft, huh? And a bit, yeah. Yes, okay. I know. Yes. Okay, that's me. Funny me. Okay. Some people on YouTube are going like, what the hell is this guy doing? Yeah? Yeah. Check this. Yeah. Okay. Alright. Anyways. Okay. Chinese. Okay. Yes. Aista. Let's go. Let's go to the next thing. I want to finish this chapter today. You know? Yes. I want to. Yes, I've been to Thailand. Yes, Arisha, I've been to Thailand. Yes, I have. Yes. Pika, I know it happens. I'm talking to my class in YouTube on Zoom. It doesn't happen for them. Nah. Yeah, he's telling me about OBS. Oh my God, you mean like this? Pika, right there. Yay! Wow, what up? Right in the middle of the screen, honey. Right in the middle of the screen, he wants me. Yeah. This is like old news, boss. Old news, eh? Old news. Let me put myself in this corner. Bottom left is a nice place to be. Yes. Oh, Dilawar, I love Turkey so much. I love Istanbul so much. I cannot do their accent. No. But I've been there 5 times. I love that city. It is the most romantic city in the world. And what good kebabs they have. Oh my God. Like, oh my God. Adana kebab. Oh my God. What a beautiful kebab. Yes. 32 times. Dude, I want what you're having. 32 times. How do you go to 32 times? Like how? Do you live in Istanbul? Oh man. Do you know what I would kill to be back in Istanbul? Oh, show off bastard, huh? Apartment and youth. Okay, fine. I'm raiding the apartment when I come next Istanbul. I love Istanbul. My favorite district in Istanbul is Karakoy. I love Karakoy. Little cafes there, the little food, the best food of breakfast. And it's right by the... So last time I was there in Karakoy, Istanbul, I got out of the... couldn't sleep, so at 4 in the morning, I got out with my friend. We both walked to the pier where at the Phosphorus River, people were fishing at 4 in the morning. Then we went over the bridge, walking to the Suleiman Mosque and did photography at 5 in the morning. Oof, nobody there. Istanbul was dead quiet. But what a place. And what am I doing this right now? We were supposed to be doing chemistry right now. We're talking about this. Oh my God. Asaki Shinji, आपको उर्दू आती है? मुझे उर्दू बिल्कुल आती है. हम उर्दू में बोलते हैं. हम पैदा पाकिस्तान में हुए हैं. Yep. You can see the bridge is amazing. Soleimani Mosque is brilliant. Absolutely. Yes. Anyway, somebody on YouTube asked me, do I know Urdu? I was like, yes, I know Urdu. Like a boss. Freaking yay. Alright, let's go back to chemistry now. Last thing left. Come on. Chop. Anyways, okay. For Zoom people, try this out. How does this look? Can you see my face now and the screen? Does this work for you guys? Mm-hmm. Yep. All right. So. Mm-hmm. 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 All right. So. Quality got a little bad. All right. Yeah, I know. This is stream versus. Let's live with this for a bit. Let's see if this works out. All right. So the next thing. साद को अब पता चला है कि सर मैं पागल हूँ. बिल्कुल साद, कोई सेन इंसान इस वक्त बैठ के केमिस्ट्री नहीं पढ़ाएगा पूरी दुनिया को ऑनलाइन. ऑब्वियसली पागल, थोड़ा सा पागल होना पड़ेगा. Thank you, Asaki. I'm glad. Anyways. Alright, so where was I next? I forgot. I was somewhere next, right? So. Yeah. Okay, so next up, right? Yes, Saad, the purpose of life is not to always earn more money. Yeah. Because there are other ways of making even more money than dancing. So, anyways. Next up. So let's dissect it a bit. Let's say, so why do we have to have this activation energy, and why does energy be needed to be supplied before it's released? Why? And for that, I want to go to a more simplified types of reactions. Those that involve, because it's not true for, I'm showing one type of reactions where I can dissect, explain to you why the energy is needed for activation energy. Simplified version. Now, for example, I have H2 and Cl2 reacting to make 2HCl. Okay. Now, I know this reaction is exothermic. It is exothermic. Some energy is released, And so the question then becomes this, that, okay, so what am I doing here? Well, first of all, you already know about the dot and cross diagram. So H2 would be something like this, and Cl2 is, in a crude way, something like this, and then you got 9 electrons, 7 electrons here, 7 here, and these guys have to combine to become two separate molecules of HCl. So 2H will overlap with the Cl new, and this is dot and cross that we've done before. So dot cross, 1 2 3 4 5 6 and 7, and then dot cross. For now, the dots are chlorines and the crosses are hydrogens. So one H2 and one Cl2 can combine to make two HCls. We know this reaction takes place. This is, you could say, a reaction to make hydrogen chloride molecule. This is the chemical change. It can also be called redox, because oxidation states of hydrogen are going from 0 to +1 and chlorine from 0 to -1. So it's also redox. We've done that bit. We've done bonding. We know they're covalently bonded. Non-metal, covalent simple molecule, covalent simple molecule. Also covalent simple molecule. So what's happening here? Well, these are what we call reactants of a reaction. Obviously, right? So when you look at the reactants, you notice that H is stuck to H and Cl is stuck to Cl. So our H ka atom is bonded to H ka atom, and Cl ka atom is bonded to Cl's atom. But here H is bonded to Cl and not another H, and the Cl is not bonded to Cl but to an H. So what is this chemical change is that to cause this overall change, you had to break the H bond and you had to break the Cl-Cl bond, and then you had to make or form HCl bond times 2, because here also and here also. Alright, now what you start realizing is that because what's a bond, by the way? A bond is a force of attraction. So to break a bond, to break bonds, you actually need energy. You need energy to break bonds. And then when bonds, so basically you can say, energy is needed to break bonds, and energy is released when bonds are formed. Meaning, even when this bond was made somewhere else in the universe, energy was released. जब ये बना था, when this bond formed, somewhere when it was formed, energy was released. Right now we are breaking this bond. Now when you break this bond, you need to supply energy, but when you make this bond, you release energy. Now on a very crude level, I mean, this is some very basic stuff, that like if I were to show you that, okay, this is H atom bonded to H atom, and when I provide energy, I can break them into individual 8 atoms, no bonds. So basically I can, in fact, I should not write this arrow. So basically I can in fact provide energy and break them, and when you can also have them combine to make the bond again. So this is bond breaking, and this is bond forming. Bond breaking is requires energy. So according to our terminology, it's an endothermic part of the process, and bond forming is an exothermic process. So okay, you're like, so what am I saying here? Well, honestly speaking, I showed you a reaction between H2 and Cl2 to become HCl. Why did I show you that? Because I wanted to map that into an energy profile diagram. What do I mean? I mean this. So the reaction I showed you was H2 and Cl2 as reactants becoming 2HCl, right? So H2 and Cl2 are my reactants. They go up and then they come down. And at the products level, you had 2 separate molecules of HCl. So 2 HCl. Now what's happening here? Well, you had to break the HH bond and you have to break the Cl-Cl bond, but you separately make one HCl and another HCl. This breaks and each H, and this breaks and each H and each Cl can combine. H and Cl can combine. Like this breaks and this breaks, these two combine and these two combine. So you have to break these two bonds and you have to form these two bonds. When bonds are broken, they give out energy. For example, in my example right here, I had to give in 436 kilojoules to break this bond. That means when this bond is made again, it's actually going to give out the same amount of energy. This is the energy needed to break this bond. But when this bond is made, the same amount of energy is given out. Meaning, even this change can be graphically represented by an energy profile diagram. That, look, I started from H2 and I can become separate H atoms. And if I go up, it is to break the bonds, it is 436. And if I form the bonds, it's minus 436. Because bond breaking is endothermic, bond forming is exothermic. Alright? Does this make sense in terms of the idea of bond breaking, bond forming? I hope it does. Hiba, I have so many videos on A2 and A1 on the channel. Please watch the videos. They'll be the same things I'll do again. There are so many videos. Please. I'm so glad, Arisha. The simple reason is, the reason why bond breaking requires energy is because a bond is a force of attraction. And to eliminate a force of attraction, you have to provide energy. And so the opposite of that happens when a bond is formed. So yeah, so bond breaking is endothermic, bond forming is exothermic. And according to this diagram now, so what's happening here in this example? So in the bond breaking parts is happening here. So in this highlighted region right here that I'm highlighting, okay, thank you Dilavar and Arisha. Let's call this section P, okay, and let's call the other section I'm highlighting, this one in a different color, I hope you can tell, I hope, is Q. Now at P section is bond breaking happening. And what's happening, which bonds are being broken? HAH is being broken to 2 hydrogen atoms, and ClCl is being broken to 2 Cl atoms. And then this is, so they go from bonds to, at this point they are literally 4 individual atoms, H, Cl, Cl, and then H and Cl combine and H and Cl combine along this path. So this section represents the energy change when the atoms are going to combine. So Q, yeah, Q would be when H and Cl combine to make HCl, and another H and another Cl combine to make HCl, which is 2 H's plus 2 Cl's makes 2 HCl's. And then this part is the exothermic part. And why? Because it's bonds formation. So this is bond formation happening here. Alright, so every reaction, you could say, has an endothermic part, which is the activation energy, and then an exothermic part. Now this is P. So my P area, the activation energy is the energy to break all the bonds. And then once all the bonds are broken, then do the atoms combine. At the atomic level is happening, is something really fun is happening. Okay, and let me show that. I actually had a nice little diagram that I forgot to show you guys. Okay, spent a lot of time finding these nice gorgeous diagrams from different amazing books, and Mr. Abul helps me do this also, and you're going to see him tomorrow with his jokes. I hope mine are better than his, but he's learning, I tell you. So this is what's happening. You had heat required to break the bonds, the atoms mixed up, and then when they combine again, heat is given out. So bond breaking is endo, bond forming is energy is being released. All right. Thank you, Samuel. I'm so glad that you will. So yeah, I should have shown these diagrams before. They are so beautiful. Oh my god. So with HCl, what was happening? I didn't have to make them myself. I should have just realized that I already have them. So basically when overall reaction happened, this is what was happening. Okay. Sorry, this is what's happening. That H and Cl's, all their bonds get broken, new bonds are formed. Bond breaking is endothermic, meaning is positive, and bond forming is exothermic and negative. And in some reactions, this part is more, this part is less. And in other reactions, this part is less, this part is more. For example, maybe for some this is plus 800 but minus 1000. So the overall change is minus 200. But for others, the up would be minus 1000, down is up 1000, minus 600 maybe. So depending on how strong the bonds are, this will vary. Okay, and we will talk about that. We will actually do questions with actual values about bond breaking and bond forming. All right. So we'll end this here, and the next part we will talk about how to calculate delta H's of a reaction using bond energies, and how to find out enthalpy change of certain reactions, also the actual values. All right. There are actually two people here who, anyways, yeah, you guys done? Yeah. What's so funny is, and it's just funny, nothing, because nothing bothers me anymore. Life is, whatever. I'm too jaded now to be bothered with life. But it's funny that people are actually sitting there, those who go on YouTube are watching this, and they have the time and to go and hit thumbs down on this video. Like, I don't know what they're expecting me to undress and dance. I don't know. Anyways, Mesam, you have a class with Sir Abul tomorrow with the same Zoom link and the same YouTube channel, and on Thursday I see you. But Abul will continue and finish this chapter's calculations tomorrow. All right? Is that all right? Thank you, guys. I had a great class. No. It's not him. No, he loves me too much. It can't be him. Anyways, so Abdul Rahim asked me, is the next chapter rates of reactions? Most likely either electrochemistry or rate of reactions, one of the two. Yes. If he didn't finish them, then maybe I'll ask him to continue with that. So I don't know what he finished or didn't finish. So yeah, if he does titration, I'll finish this chapter on Thursday then. All right. Or does he do? No, wait a minute. Does he do Friday, Saturday? I think it's me Monday, Tuesday and Thursday, and he does Friday, Saturday, right? I think that's what it is. Yeah, so you see him Friday. Now tomorrow's off and I'll see you guys on Thursday. Yeah. All right. Somebody said on a YouTube comment, hey, you sound like Bruce Wayne. I was like, obviously, because I'm Batman. I'm like, thank you, Saad. Yeah, all right, I'm glad to. More efficient. Thank you so much, guys. Love you all. Bye-bye. Khuda Hafiz. Yep. I'm Batman. I mean, like, obviously, right? Bye.